Hello, good afternoon everybody and welcome to my presentation. My name is Barbara STADLOBER and I'm from uranium research in Austria. Today I will talk about the fabrication of PVDF TrFE based devices on flexible and ultraflexible substrates and, to this end, present our Pyzoflex technology. As you can see on the background photo, Pyzoflex is based on a flexible foil covered all over with printed transducer elements. In a lot of flexible electronic applications, especially in the so-called smart X applications like smart health, smart industry, or as illustrated here, smart living, we need sensors in many places and for the acquisition of many different parameters. These ubiquitous sensors, they shall provide comprehensive support for humans, machines, and the environment. At least this is the idea. Now, to make this a reality, we need a new generation of sensors. We need sensors that can accurately measure different parameters simultaneously, like pressure, temperature, and vibration, and can transduce them into electric signals. We need sensors that can be integrated on versatile materials and free-form objects that are self-powering, lightweight, scalable in terms of area, and producible at low costs and high volumes. Ferroelectric polymers are ideal candidates for such a versatile multi-parameter sensor technology. Pyzoflex is based on these materials, namely on PVDF TrFE, a fluorocopolymer that crystallizes directly from solution in a ferroelectric phase. And this phase shows a high spontaneous polarization in the range of 100 millicoulomb per square meter. The brand name Pyzoflex illustrates the essential properties of our technology, namely pyroelectricity, piezoelectricity, and flexibility. Okay, first we have pyroelectricity, which is the sensitivity of PVDF TrFE to temperature variations, induced, for instance, as shown here, by body radiation. It is parameterized by the pyroelectric coefficient, which is 40 microcoulomb per square meter Kelvin in our printed sensors. The sensors are also piezoelectric, meaning that they react on pressure variations and on touch force, as shown here by the keypad activation. The piezoelectricity is parameterized by the piezoelectric coefficient, which is about 30 picocoulomb per Newton in our printed sensors. Piezoelectricity is also the reason for the sensitivity of Pyzoflex to vibration and structure-borne sound. In this example here, the transducer sheet was mounted on the backside of a metal part. It can record the sound of a tapping pen, so it is working as an object-integrated microphone. And finally, we have mechanical flexibility, a property that can be exploited for 3D user interaction by bending and twisting the transducer sheet. We fabricate the Pyzoflex film by screen printing the transducer pixels on the flexible substrate sheet, and we can do that in formats up to DIN A3. Each pixel has the active material, the PVDF TrFE layer sandwiched between electrodes made of PWSS, which is a conductive polymer, carbon or silver. Here you see a PET film with 100 tiny sensor spots in an array configuration with PWSS electrodes in this case and silver interconnection lines. The temperature budget of the printing process does not exceed 115 degrees, which is due to a special solvent based on gamma-butyrolactone. And this gamma-butyrolactone allows to induce high enough crystallinity in the ferroelectric layer already during the drying step. The low temperature budget enables the printing of sensors not just directly on polymer sheets, but also on unconventional substrates like paper, textile, DPU, leather, or elastomers. All of the sensors shown here are functional, by the way. As you might know, PVDF TrFE is a semi-crystalline copolymer where the ferroelectric crystallites are embedded in an amorphous matrix, as shown in this AFM image. They appear as elongated rice grains or spaghettis. After printing, the crystalline dipole moments are randomly oriented. Therefore, an electric Pauling field has to be applied in order to preferentially align these dipole moments and thus induce a macroscopic non-vanishing polarization across the layer. Under opposing electric fields larger than the coercive field, which is about 50 volt per micrometer in PVDF, the dipoles reverse their orientation repeatedly, which is illustrated here as an axial rotation of the polymer chain. This chain rotation produces a Pauling current that peaks at the opposing coercive fields. By integration of the area normalized Pauling current curve, shown here, we get the displacement hysteresis loop. It shows the typical bistable nature of the ferroelectric polarization. From the hysteresis curve, we can deduce the most important key performance indicators of the ferroelectric material sensors, namely the remanent polarization PR, which is the displacement at zero electric field, and the coercive field, which is the field at zero displacement. In this context, it is also important to mention that the polling process is a functional testing of the sensors, and thus a quality control of the printing process. So meanwhile, we do the polling in an automated form with robots, as you can see it here. This polling step can also be used to calibrate each sensor to a specific sensitivity, meaning a specific remanent polarization value. Now I'd like to show some statistics for sheet-to-sheet sensor printing. For well-controlled printing conditions, the functional yield is beyond 99%, as demonstrated here, because all of the 600 sensors printed on 40 sheets were functional, and they had less than 2% standard deviation from the average remnant polarization of 80 millicoulomb per square meter. And this is a very high value for a copolymer composition with 70 to 30. We also see less than 2% standard deviation in the measured pyro piezoelectric coefficients, which is also quite nice. The most critical process step is the drying process. Its influence on the hysteresis loop is illustrated on the left. As you can see, when going from the black to the dotted red curve, a faster drying at higher temperatures increases the remnant polarization. We believe that the fast evaporation of the gamma-butyrolactone solvent enhances the growth of crystalline regions in the ferroelectric layer. In the SAM cross-sections on the right, these regions appear as pronounced spaghettis. I will come back to that later when talking about ultraflexible devices. Moreover, by improving the drying conditions, we also observe an increase of the pyro and the piezoelectric coefficients, because both are closely correlated to the remnant polarization. We have applied the Pyzoflex technology in many application fields, ranging from Industry 4.0 over the different smart X applications like smart city, smart living, smart mobility, and smart wearables to applications in the consumer electronics field. In terms of consumer electronics, we were very active in the European project FLASHED, where we have developed different generations of enhanced and flexible user interfaces and where we have introduced novel and more intuitive gestures beyond the well-known simple touch and swiping gestures. And these more intuitive gestures are pressure-sensitive touch, gripping, and bending. A first prototype is FlexCard, which is an interactive smart card consisting of a flexible electrophoretic display from Flex Enable on top and a 3-in-5 printed input sensor adhered to the back of the display. And this input sensor is based on our Pyzoflex technology. FlexCard combines several credit and customer cards in one device. You can switch between the cards by bending. FlexCard also includes a pressure-sensitive pin code keypad, where only for the right combination of tapping pressure sequence and numbers the pin code is accepted, as you can see here. Such intuitive user interfaces can also be integrated seamlessly on 3D formed surfaces, like this 3D shaped plastic console, which has pressure-sensitive keys that are backlit. This console is fabricated by hybrid integration of printed circuitry, printed sensors, and SMD components like tiny LEDs and resistors, which are pick-and-place assembled on the flat plastic sheet with the printed components. This functional film is then brought into the desired 3D shape by high-pressure forming. Of course, here you need materials with a certain stretchability. Via vibroacoustic coupling, piezoelectric sensors can monitor the condition of machines and detect their operation mode. This is shown here for a coffee machine, where a printed transducer is adhered to the machine body surface. The sensor can clearly distinguish between the preparing, grinding, and brewing conditions by means of the mode-specific vibration pattern of the machine body. You can see that here. With regard to smart living, the Pyzoflex transducer film and a Pyzoflex electronic board were integrated directly into floorboards, thus creating a motion-sensitive floor with wireless data transmission and communication. This floor can precisely monitor the rolling of a foot when walking slowly, which is shown here. And you can see a completely different signal form for lowering the heel, which is indicated as heel down here, or for lifting the toe, indicated as toe up here. The signals are especially pronounced and reproducible for the softer 5-layer parquet. In 2017, the smart floor was presented at the Hanover Fair. Owing to the integrated piezoelectric sensors, the floor monitors vibrations and it can distinguish steps from a sudden downfall. Well, there are way more applications of the Pyzoflex technology to show, but I'd like to dedicate the last 5 minutes to a novel topic, namely ultraflexible sensors. These are ferroelectric sensors integrated on a just 1 micrometer thick paralleling substrate, resulting in devices with an overall thickness of only 2.5 micrometers. And this is so thin that the sensor film is very compliant to the skin. These ultraflexible sensors are combined here with other ultraflexible devices like rectifier diode circuits and nanogenerators, but I don't want to go into that here. The fabrication is done in a foil-on-carrier technique, The ultra-flexible sensor foil can easily be detached from the carrier and later on attached to, for instance, a 3D shaped object and other substrates. For the ultra-flexible sensors, we have performed a very careful investigation of the influence of thermal annealing after sensor fabrication. In XRD measurements, we have observed an increase of the crystallinity parameterized roughly by the height of the 110 reflection peak for annealing temperatures in the range of 70 to 130 degrees. 130 degrees is above the Curie temperature but below the melting point. The increase in crystallinity is accompanied by a proportionate increase in the remanent polarization. The change in crystallinity is also illustrated in these AFM images. With higher annealing temperatures, the lamina-like crystallites increase in size and density. When attached to an elastic material like rubber, we observe a strong increase in sensitivity upon transversal loading by a stamp as compared to the attachment on a rigid material like glass. This was also confirmed by FEM simulations, also revealing that the sensitivity increases with decreasing parallel substrate thickness. And it is also interesting to mention that the simulated strain in the piezoelectric layer is largest near the edge of the stamp. Moreover, the small thickness allows to stack multiple sensors on one another and thus multiply the sensor response, and to do that also on a 3D shaped object like this pre-bent silicon rubber. The mechanical robustness of the ultra-flexible sensors is exceptional. The polarization hysteresis remains completely unchanged during bending around an only 80 micrometer thick wire. Here you see the application of ultra-flexible sensors in a wireless e-health patch for monitoring the human pulse wave. The sensor was mounted on the neck and on the wrist. It felt nearly imperceptible. We could nicely monitor the pulse rate lying between 54 and 63 pulses per minute, and it was nearly independent of the sensor area. We could also extract an augmentation index from the ratio between the B2 and B1 peaks, and this augmentation index correlates with the elasticity of the blood vessels. By using two sensors with a defined separation, we can measure the pulse wave velocity, from which it is possible to extract the blood pressure, which is about 130 in this case. Well, this summary concludes my presentation. Pyzoflex is a printed and scalable ferroelectric sensor film with high performance. Due to the well-controlled printing and polling processes, more than 99% yield and high reliability is achieved, which enables many applications like flexible user interfaces, condition monitoring sensors, sensitive flow, and so on. Finally, I presented ultra-flexible sensors with really superior and exceptional performance.